Let's start our discussion on solute diffusion. So we will begin with diffusion in homogeneous medium before we move to heterogeneous medium. So in this lecture, we cover the basis of some notations, terminologies, and how do we define concentrations, and what is diffusion and what is convection. So when we discuss diffusion or any mass transfer, we have to know the concept of the concept of concentration. So how do we define concentration? There are two ways you can do it. You can either mass-based or molar-based. So let's think about our scenario. So you have a system. Consider a system. It can be a mix of solute. Sorry, a mix of solution. A system of volume V, so it's capital V. And there are n species. There are n species of solids in the system. So we use index I for each species. The different species can be, for example, you have sodium, chloride, or glucose, or whatever molecules. So just consider a mixture of solution and for a given volume. And there are different particles, types of particles, and we use index I. And each species has its mass, Mi, and then we also have mole, Ni. So they different species coexist in this mixture of solution. And also each species has its own velocity. So each species its average velocities. Note that velocity is a vector. Okay, so this is the setup. Now let's look at the two ways we can define concentration. The first is mass-based. So we call it rho I. Rho I is the mass of the species divided by its volume. It's same as like a density. So if you recall in fundamental physics, when we define density, it's just a mass divided by volume. So density can also be interpreted as mass-based concentration. And now we can define like what's the fraction of each species. So each species have its own concentration rho I, and then you can sum up all of the species and you get a total rho. And then omega I is the mass fraction of each species. So that is rho I of that species divided by the total rho. And then we can also define mass averaged velocity. So in this case, the velocity is a weighted sum of all the velocities. So you have the sum of omega I multiplied by Vi. So you get this V as an average. And then we also define flux. For mass flux, this is the mass density or mass concentration multiplied by the velocity of that species. So this is how we use notation for mass-based quantities. And similarly, we can define everything in terms of mole. So now we have a concentration, we call the CI. Recall in earlier lecture when we talk about like a molar concentration, or when we calculate like osmolarity type of things, we use this symbol C. And in that case, we have been using molar concentration like millimolar, something like that. And this is the same C. So the definition is the mole amount divided by the volume. And then we can define molar fraction as Xi. So it's defined by the molar concentration of each species divided by the total concentration from all species. And then we can also define average velocity in terms of the molar fraction. So in the mass-based velocity, we have V. V, it is weighted by the mass fraction. And in molar-based average velocity, it is weighted by the molar fraction. So we use V dagger to refer to the molar-based velocity. This is just to have different notation. You can call it anything. You can call it V prime or anything. We just need a different notation so that we know one is mass-based and another is mole-based. And as for flux, and this is the concentration multiplied by velocity. This is the flux of each species. So it's the same for mass-based and molar-based. It's you can see its index I means it's the flux for that particular species. So let's figure out the units of the two fluxes. So for MI, so let's find a unit or dimension of MI. So that we dimension. So MI is mass density multiplied by velocity. So the mass density is defined by kilogram divided by volume. Well, kilogram, let's use mass. Mass divided by volume. Volume is length cubed. And multiplied by velocity. Velocity is length per unit of time. So you get the dimension of MI. So you get mass per unit area squared. Sorry, per unit length squared. It is area per unit of time. Let's also find the dimension of Ni, molar flux. Its concentration is mole. Mole, let's just use mole. Per volume multiplied by velocity is length per second. Length per time. Then we get the amount of substance divided by area and time. Now recall the water flux, which is covered in some previous lectures. It is the volumetric flow rate per unit of time. Volumetric flow rate means volumetric flow rate per unit area. So it is volumetric flow rate itself is volume, which is length cube per unit time, and then that amount per unit area, which give us length per time, which is give us velocity. We discussed that water flux is velocity. So you can see these three things we analyze here, they are all called fluxes. So these are all fluxes. So you can have mass-based flux, you can have molar-based flux, and you can have water like a volume flux. All the flux have the same idea that in the numerator, you have the material you are working with. So in the case of mass flux, in the numerator is mass. If you are talk about a molar flux, then the numerator is mole. If you are talking about the volumetric flux, then the numerator is volume. The denominator is always area and time. So the flux, so for now you can understand that any flux physically defined as any quantity of material you are talking about, the transport of that material per unit area and per unit time. So that's how we how flux should be interpreted. So flux is material per unit area per unit time. And if you know this will help you to figure out dimensional problems of a lot of things when you see people talk about the flux. And then you can check dimensionality and for some sanity check. Okay, this is a side note. Okay, now we have figured out the flux, the average velocity fraction, and the concentration. Let's look at the relative flux. The relative flux are defined as the velocity of each species with respect to the average velocity. So let's look at the expression for the mass-based. The relative flux we use little j for mass-based. And if you can use the velocity of that species, which is vi, subtracted by v, that is the mass-based velocity, a mass-based relative flux with respect to the mass average velocity. And then you can also define little j I dagger. This is the mass-based relative flux with respect to the molar-based average velocity. It's a relative flux. And you can also define the molar-based flux, which we use capital J. And then we also have J, and J dagger means you can have your reference point at the bulk velocity as the mass average velocity, or you can subtract it by V dagger, which is molar-based average velocity. So the idea of relative flux is that suppose you have a system, let's say you have one flux this way. Maybe this is one species following this one. And this is, so the V, so the average velocity, these are in a reference frame. Reference frame means, so they're in reference frame. Means they are respect to a fixed frame, like in a fixed lab experiment. And the relative flux is you have the flux with respect to the reference frame. Sorry, with respect to the relative, which is not in the reference frame, which is in the in the like bulk frame. So now you have, so this is like you have species one, you have this velocity field. Now let's say you have another species. Maybe its velocity is this one. It's a little bit larger, so I'm drawing the pink line a little bit longer than the black line. Okay, now the average velocity between these two would be the average velocity would be let me see. Okay, v plus the notation isn't okay. Let me don't use black as average. Let me be good on it. I'm just saying average equals the black velocity plus the pink velocity divided by 2. Now the relative velocity of the pink. So the relative it will be the velocity subtracted by the average velocity. So you can see, maybe let's use numbers. Let's say V1 is 1 meter per second to the x direction, to the x direction. And the V2 is the pink one is 2 meter per second along the x direction. So we know that the average velocity is 1.5 meter per second along the x direction. Then the relative velocity of V2 would be V2 minus the average, which would be 2 meter per second minus 1.5 meter per second, which will be 0.5 meter per second along the x direction. So you can see the two species V1 and V2, they suppose they have the same fraction, let's say a half. Then they would as a bulk, the bulk appears as moving at the 1.5 meter per second at this velocity. And then the relative velocity would be if V2 move a little bit faster, then it will be 0.2 meter per second with respect to the bulk. And then that's also how you like interpret the flux. If you have material flux with some quantities, then the relative flux would be the flux of that species with respect to the bulk part of the average of the behavior of the entire solution. So this is the relative flux. So now once we have these definitions, let's also look at how can we write out the relative molar flux of species I relative to the molar average velocity. Okay, let's look at the quantity Ji data, which is Ci multiplied by Vi minus V data. So this is you can verify this is this equation. I'm taking this out. Why are we interested in this one? So for most of the example we are going to see for the rest of this class, or for most like common applications, people would like to use molar concentration compared to the mass concentration. That's just a convention. And so we would like to use things in terms of the molar based, and that's why we would have the average velocity also defined in the molar sense. Let me write down the language description of this one, so that you can also try to digest the meaning. This is the relative molar flux of species I relative to the molar average velocity. Relative to the molar average velocity. So this is the meaning of this expression. Now let's look at how can we rewrite this in other form so that we can digest it from multiple perspectives. And because this is a quantity, we are going to like work a lot in the future. So let's open this. So CI dagger, if you just multiply it out, you have CI multiplied by VI minus CI multiplied by V dagger. And CI here, let's just keep it CI. We will see it what is it later. In the V dagger, by definition, it is the sum of CJ, BJ divided by C. And you can see that if you take C out of these, you have CI divided by C. But let's look at the first term, CIVI. If you look at the table, by definition, this is NI. And a minus, so have this CI divided by C, this is XI. And then you have sum of CJVJ. CJVJ is NJ. So this flux, so this new formula also underscore a fundamental point. So the relative flux, the flux of a solid depends on how like its individual transport compared to its average the transport of all solids. So this is again relative flux. This is a relative flux. Actually, this is something also called a diffusive flux. Diffusive flux, if you think from what you understand about the diffusion, it's the transport of material due to concentration gradient or due to concentration difference. That's the common language that people use. And then you can write this relative flux. This is actually represent diffusion. So the diffusion part of the flux is the flux of that species minus the average flux. Like, of course, it's weighted by xi. This is how you can interpret this. But later on, we will look at other forms of it, which is more suggestive. Okay, so now this is the overall overview of our notation. This means we have n species, and the I refer to each species. So we can apply it to like 1 or 2 species, 3 species, or more species. Next, let's limit ourselves to a binary diffusion system. Or let's reduce the system to binary. Binary system has only 2 components, solute A and solvent B. Binary means you have solute and the solvent B. The solvent B isn't necessary to be like a pure water. The B itself can be a mixture of things. So it can be many compounds. Maybe B in the B is primary water. Then you may also have ions, proteins, and other solutes, whatever. The idea of binary diffusion system is that for a mixed system of complex composition, and you are interested in one of the species, we call it A, and you treat the rest of it as a background, as the solvent, you call it B. You can think in that way. So well, if you only have a pure binary system like just water and one species, that's definitely a binary system, but you don't have to limit yourself to that. What we are saying is we are just consider A in B. That's what we mean. Now in this case, let's go back to our previous equation, this equation. Let's write it in terms of the binary system. How can we write it? So the total molar flux of A, you can write it as let's see. But let me write one more step before we be doing that. Let's rearrange it. Let's put Ni on one side and then Ji the other on the other side. Let's change it up. Well, let's organize this. Okay, now let's apply this to a binary system. So then the flux of A, the molar flux of A, equals the relative molar flux of A plus the molar fraction of A multiplied by Na plus Nb. This is interpreted as this Na is the total flux. This J, A, is diffusion of flux. And this, the last term, is convective flux. It means the total transport is a combined effort from diffusion and convection. Now let's continue to write it. Let's see how do we write it. Let's keep the JA here. Let's see XA. Okay, let's keep XA. NA and B, by definition, NA is the molar flux of species A. it is by definition concentration, molar concentration of A multiplied by the average velocity of A. And then you have molar concentration of B multiplied by the average velocity of B. Let's continue to write it. It equals to this is that. Now let's pull a C out. Let's rearrange it so that now I put a C in front of this. C is the total molar concentration. X is the molar fraction of A. And if I pull out A, I need to divide the terms in the parentheses with. So what did I say? I put a C out. So I need to divide everything by C. Okay, so this is JA. Now what is CA? CA is the total concentration multiplied by the molar fraction of A. This is just the molar concentration of A. And in the parentheses, you have, so CA divided by C is XA, CB divided by C is XB. So you have velocity weighted average by molar fraction. This is molar average velocity of the bulk. So we can write it as NA. Finally, let's just clean up. Well, it's not clean up. Let's just summarize the last equation. It gives you NA equal to J A plus J dagger plus CA multiplied B. It's the same interpretation. This is the total flux. This is total flux. This is the diffusive flux. And this is the convective flux. So we will figure out in the next lecture what is diffusive flux. But for the convective flux, it's indeed it's the same like from daily life. When you say convection, what is convection? Convection is the transport of the material carried by the flow. So here you have the concentration of this species A of the solute we are looking at. And this V dagger is the average velocity of the entire solution. It's the bulk. You can understand this as the bulk velocity or the bulk motion of the system. The system means the entire solution. So if you have a concentration multiplied by the bulk motion, it is a transport carried by the convection. So this is the convection term. And diffusion, and so the total flux is diffusion plus convection. So this is the fundamental like concept of diffusion, convection, and how that are represented by the notation of concentrations. Let's look at an example so that we can sort of digest this further. For let's consider binary solution. have Ca equals to 2 mole per meter cube. And the velocity of A, it's a vector. Vector means it can be in any direction of three-dimensional space. It's in the 200 meter per second. It means it's 2 meters per second along the x direction and the 0 in the y and the z direction. So we have concentration of water B, which is 3 mole per meter cube. And the velocity of B, average velocity of species B, is 0.20 meters squared. That means it's a 2 meters squared, meter second. It's 2 meters per second along the y direction, and it is 0 along the x and the z direction. Find the molar average velocity. Velocity and the relative molar flux of A. And the relative molar flux of species A. Let's see, how do we do this? Molar average velocity. Okay, what is molar average velocity by definition? So find the molar it is V dagger defined by Ca Va plus Cb Vb divided by C. What is C? C is Ca plus Cb. Okay, so Ca is 2 mole per meter cube. Va is 200 meters second. You multiply by these two, you get 400. You get mole per meter squared second. And then plus Cb multiplied by Vb. Cb is 3 mole per meter cube. B is 0.20 meter per second. You get 0.60 mole meter square second. And it divided by Ca plus Cb. So you divide it by 2 mole per meter cube plus 3 mole per meter cube. Then you just do the math. So the numerator give you 460 mole per meter squared second. The denominator give you 5 mole per meter cube. Okay, so the molar average velocity is 0.8, 1.2, and 0 meter per second. Now we need to find the relative molar flux of A. Okay, relative molar flux of A is JA dagger. Is we had an equation for that. JA dagger is Ca multiplied by VA, subtract VA dagger If you don't know where it is, it's in the table. You can find it. So Ca is 2 mole per meter cube. And the Va subtracted by Va dagger. So Va is 200 meter per second. Subtracted dagger 0.8, 1.2 and 0 meter per second. And it gives you a flux, which is 2.4. It's a flux against it's a vector. So it has 3 directions along the x, y, z. So you have flux along the x and the y direction, and no flux along the z direction. Okay, that's how you solve this circuit. Let's look at an exercise. Let's see. What do we do? In a binary system, the diffusive flux of A relative to the molar average velocity is given by this one. So J A dagger, it is given by 1. So we give it this one. And the molar concentration of A is the molar concentration of A is 2 mole per meter cube. The molar average velocity is also given. Average velocity of the system, mineral system, is 0.50 meter per second. So here this is a let's find the total molar flux. Find the total molar flux of species A. All right, that's for this lecture.